All right, welcome everyone to Unit 6, probably my favorite unit out of all of statistics. Maybe Unit 8 is also one of my favorites, but it's really, really cool. So let's start by talking about what we're going to do, and then we'll give a cool example. This is mostly just an introductory video. So the whole idea about this unit is that if I take a sample, I'm taking a sample from the population, and hopefully I'm taking a random sample. So I'm going to randomly select some individuals or things to sample. And if I took two samples, right, if I took a sample of 50 people and then took another sample of 50 people, we would expect the statistic to be different. Okay, if I sample how many people like a certain political candidate, and then I take another sample, we should get slightly different proportions, but they should be kind of close, right? Every time we take a sample, it's going to be random. And that's what we're talking about in this unit. How is that randomness distributed? So if I take two different samples from the same population, we'd expect them to be a little different. Well, in this section, we'll talk about how exactly we can model how different they're going to be, how close together we expect them to be, where do we expect them to be centered on? And if we do a good sample, right, then we would expect our sample to have the same center as our population, hopefully. So let's get an example of what I'm talking about here. Suppose that we know the weight of watermelons on some farm is normally distributed, roughly, with a mean of 16 pounds and a standard deviation of 5 pounds. Now, this is a little small to be watermelons, but let's just pretend. So I'm going to take a sample of 25 watermelons, and I know what they average, and I know their standard deviation. Visually, we're going to use this website to help us see this. So here's the distribution of the watermelons. The mean is 16 pounds right here. The standard deviation is denoted in red by 5 pounds to either side. We know that 68% of the data should be within one standard deviation of the mean if we have a normal distribution. So this red note shows one standard deviation to either side. This is where 68% of the data is. Visually, you can see that the mean and the median will be the same because normal distributions are symmetric. And we can see that red is our standard deviation of 5. So if I take a sample of 25 watermelons from this farm, what we see here, see how we're getting these data points are dropping down. Okay, so 25 things are dropping down from the parent population. This is all the watermelons. Each block here is one of the watermelons that we selected. Okay, so all the watermelons up here normally distributed. I chose 25 random ones with this computer. We had one over here of like 8 pounds, one over here with 32 pounds, which is really rare, and I'm actually surprised to see it. And then a lot of them are kind of in this little region of near the mean of 16 pounds, but it's random, right? So even though we expect most of them to be here, notice we are getting watermelons from elsewhere. Just because these are the most likely ones doesn't mean we're only going to get ones from there. So I sampled 25 watermelons, got 25 watermelons here, and I calculated the average weight of the 25 watermelons. That average weight is this, which is maybe 18 pounds or something. So let's look at, let's take another sample, right? This sample average, X bar, this average weight of these 25 watermelons. Well, if I look at another 25 watermelons, we should expect probably a different average, right? Let's look at 25 more watermelons. Again, each thing that drops is a watermelon that we're sampling. We're going to look at 25 things that drop. That's 25 different watermelons. You see, we're getting different watermelons with different weights. And again, most of them are around the average of 16 pounds. We got a really small watermelon this time and a couple heavier ones. And now we took the sample average, the sample mean of these new 25. We took another sample, 25 new watermelon, and got a sample of about 15 pounds. And we can do this again, right? We can take more and more samples. And so what we're doing here in sampling distributions, and I'm just going to keep on playing this, we're going to get 25 more. That gives us another sample average, which is that blue block. What we're doing here for sampling distributions is how do these sample means get randomized? What's the likelihood of a given sample mean? Every time we take a sample up here, we're going to get a different sample mean. So let's pause real quick and fill in our notes. Say, okay, what's actually going on with this website? And there's a link to this website for yourself, so you can play around with it a little bit as well. So we have 3 windows. What do the windows represent? The first one is the parent population. That's up here. This is the distribution of a single watermelon. Right? Distribution of a single watermelon. That's not how you spell watermelon. That's a watermelon. All right. Whereas sample data is this middle window, and that shows the 25 watermelons that we're looking at. Which, again, the 25 watermelons, that is the sample. Right? It's called sample data. That is our sample. And again, it's their weights. And then the last one is the distribution of means that shows the average weights from each sample we've taken. Average weights. All the X bars from each sample we've taken. All right. Now, before we go on, let's look at a couple statistics. We've looked at a couple of them, but let's look at some more. Okay. So notice that each window has some statistics about it on the left. The parent population, all the watermelons. Yeah, we know the watermelons are normally distributed with a mean of 16 pounds, a standard deviation of 5 pounds. We look at 25 watermelons. It tells us the range. Remember, range is just max value minus min value. Shows us that this smallest watermelon is 19 pounds away from this biggest watermelon from that sample. And then over here in our distribution of means, this is bugged a little bit. Let's add a couple more. Okay. We took a couple more samples and got a couple more sample averages from watermelons. You can see, okay, we've taken 10 samples so far, 10 blue blocks. What was the average of all of our samples? I think it's bugging out a little bit here. Because the average is over here, but the average should be over here, right? Let's add a couple more. Yeah, now the average is getting more. Oh, interesting. Now we've taken 105 samples. Look at this shape. Yeah, it says we've taken 105 samples, and the average, the average of those 105 sample averages, so this is weird, we're talking about the average of averages. Every blue block was an average, and now we've taken 105 average watermelon sizes from a sample of 25. We've done that 105 times. The average of those is about 15 pounds. Okay, so that's the idea here. The average, this is the average, right? That blue mean up here, blue mean next to parent population, that's the average of a single watermelon. Of one watermelon. And if you're confused, you're in the right place. This is confusing, but we're doing this over time. Should get better and better. And now there's a mean next to the distribution of means that I'm talking about. This is the averages of all of our samples. Average of all our sample means. Right, we've taken 105 samples. Each sample had 25 watermelons. And we looked at the average of all of those sample averages. Right? Every time we took a sample, we found the average of all of these 25 watermelons. This right here shows the average of all of our averages. Okay. So we've done 105 samples. What if we do a ton of samples? 10,000 samples. Look what's happening. What does that look like? That looks like a symmetric graph that's roughly normally distributed. You hit the fit normal button, you can see, yeah, it's a normal curve. So we get a normal distribution if we do this 70,000 times. It's got the same exact mean, the same middle as an individual watermelon, which makes sense, right? If we take 25 random watermelons, we should expect their average weight to be about 16 pounds too. Okay, so one of the similarities is it's a normal graph. And it has the same mean. All right. But interestingly enough, the standard deviation is very different. For one watermelon, the standard deviation is 5. If we're looking at 25 watermelons, how does our sample of 25 watermelons vary? Again, if we take one watermelon, we expect them to vary by about 5 pounds. But if we look at the average of 25 watermelons, we would expect that sample to only vary by about 1 pound. So when we take a sample, there's going to be less variation because we're looking at 25 watermelons, right? They kind of average each other out. There should be less variation in what we get from a sample. So the difference is the standard deviation, right? It was 5 from the parent population, and it's only 1 for the sample one. Now, let's look at something really crazy. You ready for something crazy? And again, this is just an intro video. We'll do more in the next video, so it's okay if some of this is still not making much sense. But here's the crazy thing. We started with a normal distribution, and we got like a squished normal distribution. What if we start with a skewed distribution? What if our watermelons are skewed to the right and they average 8 pounds? Maybe they're like those like bowling ball softball watermelons. I don't know. Let's look at a different fruit that's skewed to the right. And now again, let's look at what happens if we take 25 mini watermelons. Let's also look at what happens when we take 2 mini watermelons. So let's take a sample, taking a sample of 25 mini watermelons, and we'll get a sample average just like before. All right, their average was, about 8 pounds. And then we looked at 2 more. We took another sample of 2. Their average was 3 pounds. Let's take 5 more samples of each. 5 more samples of each. 5 more samples of each. You can see now that 25, we've taken 16 samples we've done over here with a sample size of 25. And we've also taken 16 samples with a sample size of 2. Watch what happens if we take more and more and more samples. 10,000 at a time. When we're taking a sample of 25 mini watermelons, it's still normally distributed. How are our samples random? Every time I take a sample of watermelons, I'm going to get a different average. How are those averages random? They're apparently still normally distributed. If I look at 25 watermelons, those average watermelon weights are still normally distributed, even though the individual watermelons are skewed. But if I look at only 2 watermelons at a time, I'm still skewed. Okay? So sometimes we get normal distributions from nowhere. Again, you could look at that with a uniform distribution as well. Oh, interesting. We get a really nice normal distribution for n equals 25. And we get something else. This is not a normal distribution for n equals 2. All right, and you can really play around with this. You can hit custom. You can make any distribution you want. And you could see what happens when we take a bunch of samples. If the sample size is big enough, our samples are going to be normal, no matter where the parent population comes from, no matter where the single watermelon comes from, our samples are going to be normal. So let's make that a little bit more formal. Again, if n equals 2, for a skewed parent, it'll be skewed. And if it's n equals 25 with a skewed parent, it's still normal. All right, so going to introduce something called the central limit theorem, and we're really going to use it in the next video. So this is mostly an introduction. So a big definition here, and I know this video is very long because I'm just trying to really fully explain a concept. But stick with me for just one more moment and a couple more definitions. The mean, so average, of a random sample. So we're looking at a random sample of watermelons in this case. What is the average of those watermelons every time we take a sample? We're going to get a different average because we'll have different watermelons. Well, that average is also a random variable. A single watermelon is a random variable, and the average from a sample is actually also a random variable, and that average has a sampling distribution. Okay, how is that average distributed? We saw that over here. This is how an average was distributed. This is how an average with a smaller sample size was distributed. Okay, and it can be approximated by a normal model. The more the below conditions hold, the better the approximation will be. So if our sample is independent from each other, if one choice of watermelon does not affect another choice of a watermelon, that's good. If we're randomly choosing these watermelons, that's good. And sample size condition. So if the population is normal, so the population was not normal here, but it was normal here. If the population is normal, we don't need a sample size condition. You can see that here. If the population is normal, a single watermelon was normal. Whether we look at 2 watermelons or 25 watermelons at a time, the sample averages will still be normal. Both of these are normal curves. But if the population's not normal, we need a big enough sample size. Usually 30 is a good rule of thumb, but there's no fine magic number. So even if we have a skewed distribution, this is not normal. Now we need a big enough sample size for this to be normal. So this looks pretty normal with 25, but notice that this over here, this blue is not matching up with this normal curve. N equals 2 is too small of a sample size. We do need a big enough sample size if we want a normal distribution for our sampling distributions, okay? And again, next video talks a lot more about this. So stay tuned. Thanks for sticking with me on this long introduction video. We'll make a little bit more sense of this next. Bye-bye.